Good morning, everyone. Welcome to part 2 of the short course on Causal Inference. So, Sanjay will continue from where he left off.
Thank you. So I'll just continue from where I left off yesterday. I thought I'll just quickly recap the separation before I take what we did for just two or 3 minutes before we start proving it. Okay. So remember what we wanted to do was to read off conditional independence relations among random variables. Okay. But I want to read off this thing based on just the graph structure, meaning looking at the example, sorry, my seems to have crashed. Okay, yeah. There's some battery problem. Okay, but we'll worry about it. All right, sorry. So what we want to do is to read off conditional independence relations. So let me just go to where I was. Sorry about this. Yeah. So let's look at this graph. We have 6 random variables, x1 through x6, and there's some joint distribution induced by that. We don't know what the joint distribution exactly is, but this gives you some structure of the joint distribution. It says that the joint distribution among the 6 has the following factorization. It is equal to P of x1 times P of x4 times P of x2 given x1 times P of x3 given x1 and x4 times P of x5 given x2 and x3 times P of x6 given x5, right? That's basically where we were last time. We said that that's the factorization that comes. And now, given this factorization, that's all this is encoding so far. We want to see whether using this graph structure, we can also read off CI relations, conditional independence relations, okay? Meaning, are these 2 random variables independent? What I mean by independent is that, of course, the joint distribution of just this pair is the product of these 2. Or I want to read off conditional independence as well, meaning condition on some subset of these nodes. Maybe I can ask the question whether these 2 are independent. Things like that. And to do so, we came up with a bunch of axioms, rules, which were d-separation. Right now, they're just a set of rules. There is some intuition for these set of rules, as we discussed yesterday, but we haven't shown formally why these rules actually imply conditional independence. To recap these rules, the basic structure we dealt with is an undirected path. So meaning, if I want to test a property between a pair of nodes, I enumerate all undirected paths between them. In this example, there are 2 undirected paths. This is one undirected path. This is the other undirected path. Okay. And for each path, we need to reason about whether it's blocked or not. And how do we test for blocking? First, if there is no conditioning at all on that path. Okay. So in this case, this path, there is no conditioning. So if there is a collider is a node where all edges are incoming on it. Okay. So on this path, there is a collider, x5. If there's a collider, the path is said to be blocked. Okay. That's the basic rule. Okay. Now we need to reason about blocking of paths when conditioning also happens. Okay. So going back to the same example, let's look at this particular path between x1 through x4. Okay, so the graph is in this is this way. There are no colliders on this path. So by default, there is no blocking. Okay, but if I condition on any node that is not a collider, that is said to block the path. Okay. So if there are multiple nodes which are conditioned, it continues. Nothing changes. The blocking it's still blocked. Okay, so now condition on non-collider blocks the path. Now what happens about conditioning on colliders? That's the other part. So let's look at this particular graph. And I'm trying to reason between x1 and x5. this is the path I'm trying to reason about. When there's a collider on that path, we need to not just look along the path, but look at downstream of that collider as well. So we need to look at this as well. We say that if a node is conditioned on, which is downstream of a collider, then that unblocks the path. So recall that this path with no conditioning is blocked because there's a collider. But if I condition on this, or I condition on this, or I condition on this, this becomes unblocked. Those are the rules of deseparation. The intuition for this we discussed yesterday. Okay, conditioning on a collider unblocks because even if suppose two variables x1, let's look at this simple example. Okay, this is a collider. These are non-collider. These are two variables. Suppose they are actually independent Gaussian random variables. Okay, or Bernoulli or whatever you have. These are, of course, these two are independent by construction. But suppose that this variable is some function of these two. Okay, then conditioning on this leaks information about the pair of them, and therefore conditioning could correlate the two. An extreme version is what we talked about yesterday, which is the Bernoulli case. I choose a Bernoulli half random variable, so does Siva, and then Debankur simply does an exclusive OR of these two. Okay, and when he does, what I mean by an exclusive OR is if both of us are the same, he says 0, and if both of us are different, he says 1. And in this case, given my information, you can predict nothing about Siva's. But if you knew condition on Debankur, and if you know mine and condition on Debankur, you can exactly predict it. So colliders essentially, so condition on a collider unblocks. Okay, that's the intuition for unblocking. So far, good? Good. Okay, this is all recap from yesterday. I'm just summarizing where we were yesterday. So now we have got a collection of rules, which is the deseparation rules. Question is, does this imply conditional independence? Okay. So that's the main theorem. Suppose that xi and xj are graphically independent or deseparated condition on collection of nodes, meaning that condition on this, every path between xi and xj are blocked. That's all we are saying. Okay, that's what this means. Okay. That implies that xi and xj are statistically independent condition on the same set. That is a global Markov property. So we're going to prove this result now. So this I've given the reference for this. Yesterday I talked about it. This closely follows Zhang's notes and Zhang's notes. So x1 through xd are nodes on a DAG. I'm only dealing with directed acyclic graphs. Okay, and let script x be some subset of these nodes. Some basic definitions. What's a leaf node? It's what all of us know from graphs. It's a node with no children. Okay, so in this graph, this, and this are leaf nodes. Second definition is the ancestor of a set. The ancestors of a set are those variables along with all its upstream nodes. Okay, that's what is ancestors. So in this example, for this node, this is an ancestor. This is the ancestral set for this. This is for this node, the x3. There are 3 ancestors itself and its 2 parents. This one is not upstream because you have to change directions. So this and this are incomparable. So this is ancestor set. Okay, it's all very reasonable definitions. So I'm going to talk from now on about upstream and downstream. The meaning is very clear. When I talk about downstream, I mean starting from this, going all the way down, and upstream meaning going up. I shouldn't turn around and go back down somewhere else. That's all upstream is. Okay, good. A collection of nodes is said to be ancestral if the ancestors of x is x itself. So if, for example, this graph was only this box and these nodes were not there, this would be an ancestral set, as an example. If there was one more node, this also would be an ancestor. This would be an ancestral set if I had this. Okay. So All right. So we have the basic definitions: leaves, ancestral, and ancestral. The first result. So the first couple of lemmas are rather straightforward, but let's just go through this anyway. The first lemma is about, lemma 2 is about marginalizing. So I have a collection of nodes x1 through xd. Okay. So that's my G. I remove one node from that graph, let's say. It's a leaf node. Xk is a leaf node. So basically I look at this and dump this. Okay. And my question is, look at the joint distribution on this collection. And look at the joint distribution on this. Okay. What can I say? Well, the claim is, if I look at the joint distribution on this, but restrict it only to this, they're the same. Okay. Why? If you think about it for a minute, it's clear. The joint distribution on the restriction G prime is nothing but the joint distribution over the whole thing. You just marginalize out this one thing. Meaning, you look at the whole joint distribution on G and look at that one leaf node and sum over all possible values of the alphabet of that. That's all it is. It's clear? Okay. But this last node has no children. So immediately this follow. So you can. So in particular, it's not a parent of anything else. So I can write the joint distribution of G prime as the original joint distribution times just that one term, P of xk given its parents. And when I sum over all its values, it's just one. So I'm just going to recover the rest of it. Okay. So this is not difficult at all. I'm just stating this. So the second is, suppose X is an ancestral set. Okay. And G prime is the DAG with all nodes outside X removed. So I have a graph. I have X is ancestral. There are a bunch of other nodes as well in this graph potentially. I prune all the others out. Then again, the same property holds, that the joint distribution of a joint distribution, the joint distribution on just the nodes X with the original graph is the same as that of the pruned graph. And the proof is again almost immediate. You start from a leaf, prune it out, then go again, prune it out, then prune it out. Each time you prune, nothing happens. And what you're going to be left with is the ancestral set. Okay? So it's longer to write it out, to be honest, than to just say it. Okay? So these are two immediate results. All these two allows us to do is, I just need to think about ancestral graphs now, okay, for whatever proof we are going to. That's really all this is setting things up. So now let's get to the main idea. So the first result is the following. Suppose I can partition the collection of nodes into three sets, X, Y, and Z. Okay. So this is a partition, meaning that there is nothing left over. Okay. Suppose that in this case, the following properties hold. Suppose the set X is D independent of a set Y given Z. So there's a bit of overloading of notation here. We talked about deseparation of pairs of nodes. For sets, it means for every possible pair from each side. Okay. So meaning, if there's just one variable here and one variable here, what it means is that every path between this variable and this variable is blocked when conditioned on this. When there's more than one here, I need to test this for everything. That's all this means. This is a set-wise extension of the same definition. Okay. So suppose that a pair of sets is deseparated, condition on Z. That implies that they're actually statistically independent, condition on Z. The proof is the following. Let's draw a picture. So this is the set of, I've just drawn this bubble to represent all possible variables. The stuff here are the X variables. The stuff here are Y variables. And I'm going to partition this conditioning set into two parts, Z1 and Z2, to be different, which are which such that Z is Z1 union Z2. So it covers all the variables and they're disjoint. Okay. So so Z1 and Z2 is a partition of Z, and they're constructed in the following. Look at Z1. Z1 are all those nodes in Z such that at least one of its parents is in X. Okay. So if you have a node here, that means there must be a directed edge. It may have multiple other things. I haven't specified anything about the others, but at least one. Maybe it has more than one as well. So any node here has one parent here. I haven't told you anything about what else can happen. Okay? That's what Z1 is. And Z2 is everything but Z1. Okay. So two immediate properties. Look at any node in this set. Okay. Its parents, any node in this set, has parents in only this set. That's the property. Let me draw this again. Look at any node in this set. Its parents cannot be here. That's what I'm saying. Its parents must be here. Why? Let's look at this node. Okay. So it has one, we know that it has one edge in here. Suppose there's one more here. Then this node would become a collider, and there'll be therefore it'll open up between these two. But that's a contradiction. Let me repeat. Let's pick any node here. It has one edge here. Suppose this was also there. Then this would be a collider, and it'll open up a path between these two. This path will become unblocked. And that cannot happen. Because condition on Z, we know that all paths between X and Y are blocked. Okay. So no nodes here can have parent. This is not allowed. So this is what it's shown. This is not allowed. Of course, this is not allowed either, because otherwise there's an immediate path. Okay. So this is property A. For any W in X union Z1, all its parents are in X union Z. Is it clear? Right. Second, let's look at any node here. Y union Z2. Okay. And the claim is none of its parents are here. Same reason. Okay. Because by construction, by definition, this does not exist by construction of Z1. Z1 is defined as all of these Z's where this exists. So this does not exist by this definition of Z1. Okay. And yeah, that's basically it. So this green picture, this picture in red and green summarizes what we are seeing. So we know that anything in green is possible. Okay. Anything is, more importantly, the reds are not possible. So that's what we have proved so far. So now let's put these things together. So I'm looking at the joint distribution of P of X, Y, Z. So that means because of factorization, it's a graph. Because just the graphical representation is a P of any node W in X union Y union Z given its parents. That's the definition. I can split up Z because the partition into Z1 and Z2. Okay, so it is P of W in X union Z1 or W in Y union Z2. From A, for X union Z1, none of the parents is in Y. Okay, so this is some function of variables only in X and Z. For this part, from B in Y and Z2, none of its parents lie in X. So that means this is some function of Y and Z. So what we have shown is that P of X, Y, Z can be factorized as some function of X and Z and some other function of Y and Z, which means from our lemma 1. So this is the characterization of conditional independence, which just the Markov chain, which was satisfied. This X and Y conditional independence is given Z. Okay. So it's an immediate proof. It's not that hard. Okay. It's once you draw the picture, you're done for a partition. Okay. Now let's go beyond. So now we showed if you have a partition, this is what you have. So the main theorem is a global Markov property, which says that let X and Y be variables in a DAG and Z be any other set of variables. So we don't have a partition. X and Y condition independent given this set Z implies that a graphically deseparated given Z implies that X and Y are condition independent given Z. This is the main theorem. First, without laws of generality, we can assume that the nodes we care about are just X, Y, and look at X, Y, Z, and look at the ancestrals associated with it. But prove out everything else, it doesn't matter. Okay, that's what basically our first two lemmas were talking about. So I can just recursively start proving things out and just work with that set of nodes. Now, in this collection of nodes, I've got X, Y, Z. Okay. Let's define script X as all those nodes which are not deseparated from X, condition on Z. So this is a conditioning set in the middle. Okay. All these here are those which are not deseparated given Z. Okay. That means there's an unblocked path. For anything to here, there's an unblocked path. Okay. That's what this is saying. And Y is all the remaining nodes. So the claim here is that this and this are deseparated given this. That's first claim. The second claim is these three form a partition. Forming the partition is trivial by construction. The only thing that we need to argue is that these are deseparated. And again, that is straightforward because you know that there's a path here from this. That's what from any other node. If there's a path there, then I could just go unblock path there. You could go there, and this would not be that will violate this construction of X. X is all those nodes which are not separated. So Y is separated. Okay. If there was a path from this to this and then this to this, then I would actually have put that into this bucket. Right? That's all. That's essentially the reason. Question? It's okay. So I've written a paragraph to explain that, but that's basically all that's happening there. Okay. Therefore, from now we can use our previous theorem. Now there's a partition, and therefore X and Y are condition independent given Z. Now all that's left is to sort of look at. So now we have shown that this set and this set is condition independent given this. We need to show that this variable and this variable are condition independent this, and that's just marginalizing. Okay, and the proof of that is pretty straightforward. I'm just saying it's just marginalizing, but I thought it may be good to just write out what I mean by just marginalizing. Okay, so X prime is everything in X in the set X other than the one node I care about. Set Y prime is everything in the set Y with removing this one node. Okay. So we know that the set these two are condition independent given Z. These are sets of variables. Okay. What does it mean? That means there are some functions P1 and P2 such that if I look at the probability of the intersection of AI, where AI is a random variable xi takes value little xi, it can be written as the P1 of the variables in X and Z, P2 of the variables in Y and Z. So if I care about just one variable in this set and one variable in this set, okay, look at the joint distribution of that one variable, and the conditioning set. This is the set of nodes you're conditioning. Okay. Then what I need to do is to look at this and just marginalize out all the other variables in X and all the other variables in Y. Okay. And so now this does not depend on X prime. This does not depend on Y prime. So I can just move this inside. This is yet another function. This is yet another function. And that's all there is to it. So this, I wanted to just show this. This is obvious, but this last part, but it's worthwhile to see it because this result is quite nice. This factor showing this characterization of joint distributions using the existence of functions is actually useful for proof. You can do it other ways, but it'll be much longer. This just gives a 2-line proof to do things. Okay. All right. So, yes.
Did we use all the 3 properties that you used in the definition? In particular, the conditioning stuff. So can Z be null set here in all the theories?
Yes, it can be.
Okay.
It can be null set. So we have, yeah.
And then for a non-collider, you had a property for a definition of blocking. Did we use that?
Yes. So yeah, you can go to. So on this side, I have written notes on other cases and where things could break, and you will see that it doesn't break. So I didn't talk about it, but you can look at my examples on this side to see what exactly the question. So this says what we have said is using those properties, we have done this. But your question is this really the minimal set of properties needed? And so go through those examples on this side and you'll realize it. That's what I've written. There are 2 examples I've drawn. That green example is a good one to think about. And let me see. So I had the same question when I was thinking about this. And so this picture here is the canonical example you want to keep in mind when you try to break those conditions. Okay. Okay. So what we have shown is deseparation rules imply conditional independence. For those of you who have worked with undirected graphical models, okay, for undirected graphical models, what we had, we have this notion of a Markov blanket. I'm talking about directed here, but many of you have presumably seen undirected models. What's a Markov blanket? In undirected graphical model, we know that if you look at any collection of nodes and look at a one-hop neighbor outside it, if you condition on that, then what's inside the blanket and what's outside the blanket are condition independent given this collection of nodes. The Markov blanket here is somewhat different in a directed graphical model. So it's worthwhile to think about this. So look at this node X. I want to understand what the Markov blanket is. The Markov blanket is defined as its parents, its children, so they are one-hop neighbors, and the parents of its children. So you need to go back up one step. Qualitatively, why? Let's start with that before we get to we prove anything. The reason is, let's look at this node and this node. Conditioning on this unblocks this. It's a collider. So this path immediately opens up as soon as I condition on this. So to block it, I need to find another node and put it in there. Okay. So now this is a blocker. So that is why the Markov blanket for directed graphical models is not just one-hop neighbors, but the parents of the downstream nodes as well. Okay. So when you're reasoning about directed graphical models, keep that in mind. It's a slightly different notion from undirected models. Okay. So that's the definition of Markov blanket. So let B be the Markov blanket of X and Y be any other set of nodes. Then X and Y are condition independent given B. The proof is immediate. I essentially showed you why. It deseparates. So that's why deseparation is it's very useful to reason about condition independence just using this graph now. Okay, that the global Markov property implies this. Okay. So there's something called the local Markov property. The local Markov property says the following. Any node X is conditionally independent of all its non-descendants given its parents. So now I'm not conditioning on the children. I am just conditioning X on its parents. That's all we are conditioning. Then it says condition on this red box, X is conditionally independent of these three nodes. Okay, they are the three non-descendants here. Why? Okay. Look at any path between a node, one of these non-descendant nodes, and X. Okay. There are two ways you can get to that path. Either go up or go downstream. If you want to go up, the parents are blocking it. So you got parents are blocking everything that's going upwards. If you go down, children become colliders. And I'm not conditioning on the children, so the colliders are blockers. Okay. So you cannot go this way. So that's essentially the proof. Okay. So we have now the global Markov property, a definition of Markov blanket, and a local Markov property. So the theorem connecting all this is the following. Let's have a DAG and some joint distribution associated with it. The global Markov property, we've already seen, conditional deseparation implies conditional independence. The local Markov property is X is independent of its non-descendants given its parents. The third is a Markov factorization property, which is the graphical model description, that P has such a factorization. This is completely algebraic. It says that the joint distribution P has a factorization that is consistent with the graphical model you have drawn. Then the following theorem is true. One, if and only if two. Okay, that's first statement. And three, under some technical conditions, the if and only if holds true for 3 as well. And the technical condition is the following, that some absolute continuity is needed for the distribution. You shouldn't have like a zero mass and things like that. Okay, so meaning there is some on these variables, x1 through xd. Remember, that's what we are dealing with. There are a bunch of variables. For these variables, there's a product measure, okay, such that P is absolutely continuous with respect to this measure. All it's saying is that you don't have sort of singularities and things like that. There's zero. This is also true for continuous, which is why we have written things more carefully. But discrete, all it means is there's no zero probability stuff. When you're dealing with densities, you need some absolute continuity. So this is proof. I'm not going to talk about it. I want to move on to other things. But the paper I like for going to all this stuff is this: Independence Properties of Directed Markov Fields by Lorenzen et al., Networks, 1990. Just as a side comment, at least I couldn't find this on the internet, Googling around for this thing. So I actually got this scanned at the library. I have a PDF now. If anybody's interested, I have a PDF copy of it from the actual book. And if you're interested, just send me an email. I'll be happy to share this paper. But it's a nice paper to read if you're interested. It also gives you this paper is interesting in the sense that it also tells you if you don't want to do deseparation, but you want to use a different equivalent form of reasoning on graphs, that's the paper that introduces the other ways of graphical reasoning. So it's interesting to read that.
So do you need this technical condition for both directions to include 3 or one of the directions?
Good question. I don't remember now. I think it's only for one of the directions, but I've just put it this way for both directions. Yeah.
So in the first line of the theorem, you said P is joint distribution associated with it. What does it?
Oh, all I'm saying is there's a graph is just a collection of nodes,
Sure.
but these are random variables. So there's some joint distribution on those D random variables. P is the joint distribution of those.
So 3 implies 1 is straightforward. We are using it in the proof of global market
Yes.
property, right?
Yeah.
Okay.
Some of these are straightforward. There's just one of this which requires calculation among these three loops. I forget which one. Okay. This is also immediate. This is what is used to prove this. That's why that's introduced here. And then you use this to prove this. As far as I remember, the proof actually goes that way, which is why I was a little hesitant about Debanko's question about one way or the other, because I think the downstream actually is, you don't need anything. That going there upstream actually requires this absolute continuity. But I haven't read. I read it some time back, so I don't remember offhand. Okay. Next, we'll move to Markov equivalence of DAGs. This also relates. This is going to actually come back later regarding the question you asked just before we started, which is about learning. Okay. So right for today, I'm going to talk about reasoning on a given graph and given the joint distribution. But what we care about, many of us at least care about when you're doing learning, is to actually learn the structure of this graph or reason from data. So what can you learn? So then it turns out there's some limits to what you can learn from data, and this definition is going to be important for that. Okay.
So does this big theorem imply the converse of the global Markov property?
No, I never said that.
Oh.
I never said that. We'll come to that. That's a very good question, and I'm punting it to 5 minutes from now. Okay. Right now, all we have shown is one direction. It's not there's no if and only if. For between graphical reasoning and conditional independence, we have just gone one direction. Okay. This big theorem says various other properties are equivalent. That's all. So next, Markov equivalence of DAGs. So I've given you a graph, VE. Let capital mu of G be the set of all distributions that are consistent with that graph. What do I mean? So you're given a graph structure G. Look at a joint distribution. P is some function of x1 through x, some function over the alphabet. Okay. And this joint distribution, suppose it has the global Markov property with respect to G. Okay. So there are many joint distributions that will have, which are consistent with that graph. Then, so that's what we are defining as mu of G. Now, Markov equivalence of graphs. Two DAGs G1 and G2 are Markov equivalent if the set of distributions associated with them are the same. I thought this figure, you can read much more in the text, as well as I have additional notes in the, I'm not going to talk about these additional notes, but I've just dropped it off in the Dropbox. This picture shows you two graphs which are Markov equivalent. Okay, these two are exactly the same, except this one has the edge this way, this one has the edge that way. Okay. Turns out that these are Markov, G1 and G2 are Markov equivalent. Okay. I'm not going to calculate it out and show it to you. You can play with this offline yourself and check. Okay. Why do I care about that? Well, so let's define one more thing called the skeleton. The skeleton of a DAG. So these notes are not consistent with what is online. I changed these last evening, some ordering. So what you're seeing in your, maybe when you're looking at the PDF, I'll upload I reorganized things last night. So that's why it's somewhat different. If you look at the skeleton of the DAG, the skeleton is simply take every edge and just replace it by undirected edge. So this is the skeleton of this graph. Finally, we'll talk about an unshielded collider or an immorality. An unshielded collider is the following structure. If you look at a graph where you find a node and look at its parents, but there's no edge between its parents, then this is called an unshielded collider. Okay. So I want to look at this. It's also called the V structure. Okay. These are all the names for this. It was called immorality. It's been called unshielded collider. It's called a V structure. All these are exactly the same things. So we talked about Markov equivalence of a pair of graphs. Okay, G1 and G2 are Markov equivalent. We saw if this set of distributions that are associated with each one are the same. So this automatically gives you an equivalence class. The Markov equivalence class is the set of all DAGs that are Markov equivalent to G. Okay, you give me a graph, look at set of all other graphs that have the same that have the same set of distributions that are associated with. That's a Markov equivalence class. And the lemma is the following. G1 and G2 are Markov equivalent if and only if they are the same skeleton and the same immoralities or the same V structures. Okay, that is the again, from now on, I'll not prove many of these things because this is a short course. I'm going to state these results. So basically, this one, this is the V structure here. This is a V structure here. So in the V structure, it's exactly the same. And the skeleton is exactly the same if I remove the directed edges. Okay, meaning this change has happened on an edge which is not part of a V structure. Okay. In which case, you can represent this class by the following figure. You can, for the whichever edges are common on all of these, you put that in. But whichever are potentially have different directions, you put by undirected edge. This is called the CP DAG.
Sorry, question?
Yes?
Question on Zoom. Isn't there another V structure on the graph on the right with X2 having
Actually,
two
you're right.
parents?
Sorry, absolutely. Thank you.
That's not common.
Thank you. You're absolutely right. There are two V structures here. There's one V structure. There's a second. No, this is not a V structure. This is not a V structure because there's a
in
parent.
G2, X2 has two parents, but that's not common to G1.
G2, X2 has G1.
Oh, two children. Okay, sorry. Or no. You sorry. Take that back.
Okay.
I take that back. Sorry.
Okay. Yeah, there's just one V structure here in this thing. Yeah, thanks. So what's a CP DAG? A CP DAG is a completed, partially directed acyclic graph. All that means is the following. Keep the V structures common. Keep all directed edges which are common, keep it there. And wherever things differ, replace it by undirected edge. So right now I've just defined this and I'm moving on. The reason that this definition is there is later we'll see when we are doing learning tomorrow, we cannot learn beyond CP DAG. Given a G, from data, you can only learn up to CP DAG is some a basic theorem will deal with it. Okay, so this answers this. This is why this is introduced here, but it's just left dangling. We'll come back to CP DAGs when we actually learn from data.
So in the previous example, so X3 was not a V structure, right? So
give me a second. X3 is not a V structure.
Yeah, so X1, X3, that age is still kept with the direction. So what was the rule? Like anything that
I just drew an example here. Maybe there is some other graph with or without. From just these two, I drew this thing. That's all. A CP DAG says that you can learn up to the Markov equivalence class. So really, we see that all graphs with the same skeleton and the same immoralities. That's all. That's why lemma 4 is really the one you want to look at. Okay. So all V structures will be exactly the same, and the skeleton will be the same. But that's basically all you can figure out in general. I'm going to skip the definition of causal minimality. You can read it because I'm never going to use it again for what I'm going to talk about. So I want to spend some. We'll just stop for 30 seconds. Somebody is coming in. I'll continue in. I'll just stop for 30 seconds. Pardon. Shall I just continue?
Yes.
Okay. All right. So let me continue with a very important thing. This is going to come up later is faithfulness. What we talked about is if you have deseparation, that implies conditional independence. Ideally, you'd like to go the other way. So let's see why you'd like to go the other way. If I am given data and I want to learn the graphical model. I want to learn the structure. Then the only statistical tool I have in hand is a CI tester or conditional independence tester. Meaning I can implement a black box which says, I'll give you basically a table. I want to data from X is in column 1, data from Y is in column 2, and rest of the columns are Z. I want, given this this data set, I want to figure out whether column 1 and column 2 are condition independent given the rest. Okay. There are black boxes that can implement this. We'll come to this. This is going to be Friday. We'll spend at least an hour talking about CI testers and what kind of guarantees you can give for these kinds of things. Okay. But this using such a tool, can you actually figure out the structure, learn the structure? This will require somebody to go the other way. Okay. From CI, you want to learn structure. And ideally, we'd like to say this statement is if and only if, but that's not true. So we make an assumption. A graph is said to be faithful if the other direction goes. It's not a proof, it's in English. Okay. Faithfulness is an assumption. We'll talk about faithfulness violation and talk about issues regarding that in a minute. Okay. So let's look at this graph. Forget G2 for a second. Just look at G1. So X, Y, and Z, X is just a Gaussian, zero mean unit variance. Y is A times X plus an independent Gaussian. And Z is C times X plus B times Y plus an independent Gaussian. So this is my generative model. Okay. This is the graph associated with it. Suppose we have that C equal minus AB, meaning C plus AB is 0. Okay, suppose we had that property. I chose these parameters so that this is true. You can check that X and Z are uncorrelated, and therefore these are all jointly Gaussian, they're also independent. Okay, you can just check this thing. This is a simple calculation. I think it's there on the B notes. I've done this calculation, but you can check that. But of course, X and Z are not graphically are not deseparated. Okay, so here's a break. Even though I have conditional independence, the graph does not show that. And this is really the issue, because all along we know that conditional independence is really an algebraic property. Independence or conditional independence are algebraic properties of distributions. Graph structures shouldn't hold all, it's a very structural view of this thing. So there must be a gap. It's clear if you just think about it. And here's an example. One could argue, however, that this is just a zero measure set. This is just in the set of R3, you're looking at sort of all parameters C, such as C plus AB equal to 0. So maybe you don't care. And for a lot of the sort of distribution-based causal inference literature, faithfulness is just assumed without too much worry. Okay, because after all, it's just at least in the Lebesgue measures, a zero measure set. You shouldn't worry about it.
So Gaussians have this property that correlation and independence, uncorrelation and independence are the same thing. So is that required? So is this the only kind of example?
No, you can. There are lots of faithfulness violations. I just pulled one out to show this thing. Okay, I'm faithfulness violation actually, in my opinion, a big problem, but we'll get to that in a minute. Okay, I just wanted to. So what does it mean? From data, you can't distinguish between this and this. Okay, that's what the second graph is. If these parameters are chosen appropriately, and these are chosen appropriately. Okay. I want to make two remarks. The first is that for most of the time in over the next couple of days, except in one case, I'm going to assume there are no latents. What is a latent? Suppose that this is the graph. So latents will be represented by dotted lines around variables. It means that this is a joint distribution, but you can only have observations on this triplet. Okay, that's a latent. Okay. But the true graph is this. So what does it mean? That means the joint distribution XYZU is P of U times P of X given U times P of Y given U times P of Z given XY. But we only have access to the distribution PXYZ. Okay, that's all it means by latent. In the infinite sample setting, that's all it means. The problem is DAGs are not closed under marginalization. Meaning, PXYZ does not need to have a Markov factorization that encodes the independencies under the original DAG. Okay, that's what I mean by it's not closed under marginalization. You can read Silvan Garamani. There are a bunch of papers below I have given. You can read much more about it. I'm just sort of pointing this out. I'm not going to go down this road, but this is just a. Okay. So what do? There are other graphical models that are closed under marginalization and conditioning. So we have talked about one graphical model. Are there other types of models you can have? Yes, more complicated models. There's a zoo of them. And you can look at some of these papers, the hidden life of latent variables in JMLR, the graphs for margins of Bayesian networks, etc. And Pearl's book and so on. Again, I'm not going to talk about these issues, but when you have latents, which happens all the time with real data, you need to worry about these issues. I'm just not going to talk about it. That's all. That's the first remark. Second is faithfulness is a strong assumption that is going backwards from conditional independence to graph structure. It looks like it's mild because, in R3, at least the example I showed, C plus AB is 0 is quote unquote a 0 Lebesgue measure set. Of course, what it means, pushing something off saying it's 0 Lebesgue measure is scary because why is Lebesgue measure so magical or why is that problem? That's a different story. Okay. But at least at some level, it looks like I shouldn't worry about it. However, there's this very, very nice paper by Uller, Raskuti, Bullman, and Yu, Annals of Stat 2013, which I'm oversimplifying it. But essentially, it says that look at sort of structural equations, structural causal models, or ACMs, essentially graphical models that are close in some sense to ones with faithful violations. It's a large constant fraction of all linear models. Okay. So, which means that in a finite sample setting, distinguishing noise and CI is actually very hard. And this is going to cause a lot of trouble when you actually want to do data dependent. So the samples needed to actually figure things out can be humongous sometimes. So this is a well-known issue when you're sort of developing causal models from data. Okay. So I would recommend that you look at this paper. It's a really nice paper to read in this space. Okay, so that gives me enough graphical models language to actually get back to causality. Oh, sorry, I went 5 minutes over, but this is a great time to stop. So we'll take a 20-minute break and they'll continue. So the next piece is actually coming back to causality. We will continue at 20 minutes from now, right? 11:15 here, local time. So I'm stopping I'm muting the microphone. Okay, thank you. Let me continue from where we left off. So we talked previously about graphical models. Is the sound coming through? I just switched on the mic, just making sure everything is okay online. If it is, could somebody give me a thumbs up or something like that? That'll perfect. Thank you. So now I'm going to switch. That's basically all the plumbing of graphical models that is needed. I want to switch back now to causality and causal models. So now we are going back to sort of the books, Element of Causal Inference and the causality books. So let's start with the basic model, structural causal models, SCMs. So what we have, we start with a collection of random variables x1 through xd, and we say that it's defined by a structural causal model C if the following is true. So for each variable xj, we define a collection of variables we call the parents. I mean, from all the stuff we have seen in the graphical models, we see where this language is coming from. We define a collection of variables called as parents, and an independent random variable nj, and some deterministic function fj. Okay. And we assign xj as this is the structural assignment fj of it's a function of these parents and this independent random variable, where parents are simply some subset of x1 through xd other than xj. We also assume n1 through nd. So there are d variables. So there are n1 through nd random variables. We assume that they're mutually independent. So, and we further assume that the parent structure is such that the induced graph is acyclic. Okay, so we have a directed acyclic graph. It corresponds to, so given the structural equations, you can figure parents for each node, put this whole thing together as a graph. I'm going to assume this is a DAG. Okay. If it is not a DAG, then read the text. There's more issues. I'm not even going to get into that. I'm going to only stick to DAGs in this discussion. Furthermore, these equations induce a joint distribution on x1 through xd because of the independent random variables n1 through nd. From that, you can find a joint distribution. So we'll denote that probability measure induced on x1 through xd by capital PC and the actual joint distribution by little pc. Either discrete or continuous, I'll abuse a notation, call all of them little p. Okay. I'll also abuse notations for marginals as well, meaning PC of x1 through xd is a full joint distribution. PC for just one x1 is a marginal. If depending on the number of variables, I will just use the same function. Those, honestly, I should use different indices for each one. I'm just abusing notation so you can just see from context what I'm dealing with. Okay. For example, here's a structural causal model. Here's the DAG associated with it. X1 is some function of noise, N1, random variable. X2 is some function of X1, X2. So X1 is that one. X2 is some function of X1 and N2. So you can go to this one and find this one. So essentially, I'm constructing a joint distribution by just going down this. Then X4 is an independent one, N4. Then X3 is a function of X1, X4, and N3. So given I know these things, so I can find the conditional distribution. X5 is a function of X2 and X3 and N5. So given this, I can construct this graph, and also it gives a joint distribution. In terms of language, the parents sometimes are called direct causes. If you look at the causality language, that word is also used. So what is an assignment versus an equation in a structural causal model? These are said to be assignments in the sense that I am allowed to change one or more of these equations, and these are called interventions. I can take this equation and change it, for example. What does it mean? I can say that I will replace this by a constant A, say. Okay. What does that mean? If I replace this by a constant A, the model changes. That means I've basically deleted this edge, and set this to A. Okay. It's a new model. As soon as I change one of these structural equations, it induces a new model and a new joint distribution. Okay. So interventions are now described going back to the SCM, structural causal model. I start with the structural causal model that generates my original data or my original observational data. And any intervention is one or more changes in these equations. And such that still the DAG structure is preserved. For example, if I take this and put some other function F7 of all the variables, the DAG structure will be broken. So that is not allowed. Okay. So those are the kinds of restrictions that are there. So formally, I take xj is some function of fj, its parents, and nj. I'll replace parents j by parents tilde of j and some other independent n tilde j, which is some new random variable, which is independent of n1 through nd. Okay. This is an intervention. This is what is formally defined as an intervention. So SCM's structural causal model is often also denoted by S, Pn, where S is the structural equations and Pn is the product measure over N1 through Nd. Because once you have that distribution over N1 to Nd, they're independent, so it's a product measure. It fully specifies the joint distribution of the random variables. Is it clear? This is the basic model. So this is the first time I'm introducing the formal model of what a causal system is. Okay. The proper proposition, again, from now on, I'll not prove most things. I'm just going to talk about things. Few things here and there I'll prove, but mostly not. The proposition is that the structural causal model induces a unique joint distribution over x1 through xd. And this is called the entailed distribution. Think about it, this is rather immediate that because you see, once I have this, there's a directed structure. So if I just do the lexicographic ordering on it and just go down and just go through these equations, I'll get the joint distribution, and that should be unique. So you can see that the proof should follow. And furthermore, the SCM implies the Markov property. Okay. So because PC is a joint distribution induced by an SCM with a graph G, then PC is globally Markov with G. Again, it's almost immediate. So this is so starting from the SCM, now you can connect back to everything we have talked about with directed graphical models. Okay, so this is essentially the basics of what this is just a language. From now on, I'll be talking about SCMs and entailed distributions and interventions defined by changing one or more equations in the structural causal model. So let's go back to our example one, Bennett versus ring, right? So at least the way I described it there, we need to test the direction of causation or to correctly interpret the kidney stone experiment when we did the Simpson's paradox yesterday, any of these things, we needed to do additional experiments. And now we can see what those additional experiments mean. That means you're changing the structural causal model by one or more, and then collecting data from the structural causal model, and then reasoning about the existence of edges. So in this section, there are two goals. First is defining interventions through a family of structural causal models and their corresponding tags. So you start with an SCM, you can define interventions, that gives you a new SCM. So you get a family of SCMs corresponding to the original model and all the interventions. And two, can we do the total probability theorem kind of things for this? Meaning, I want to compute interventional distributions. So I start with one SCM. Suppose I have access to the joint distribution for that. I decide to change one or more equations. So now this is a new joint distribution on the collection of variables. I want to see whether I can compute the joint distribution on the variables, but from data of the original observational distribution. Okay, so I don't want to really do any new experiments. I want to only do thought experiments. Clearly, it is not always possible because I can take an SCM and change every equation to something completely different. And this is going to give me an arbitrarily different graphical model. So you cannot do this, start from one and figure everything else out. Okay, so we want to see some sufficient, first, what the roadmap for this piece is, sufficient conditions, then towards the end, necessary and sufficient conditions. So this is, I just copied this from the notes we just saw a second back. This is what we are going to call the observational structural causal model. The first model you start with, meaning xj is some function fj of its parents and some independent random variable nj. Okay. And these noise are mutually independent. And of course, the graph is a DAG. Notation, P script C is a joint distribution, or is a little P script C is a joint distribution on the original causal structural causal model, on the variables defined by the original structural causal model. Intervention, we take one or more of those equations and replace it by potentially a new function, new parents, and a new independent random variable. So it's going to give you the intervention, and that will give you a new interventional distribution, C tilde, over the same set of random variables, x1 through xd. Okay. So we have the C tilde. I'm going to introduce a notation now. So the joint, because we changed one or more equations, we got a new model and therefore a new joint distribution. The way it is related to the original model, and we are going to encode that by the following notation. The C is the original model, and what we are doing is a change in the equations. That's this do, okay? And what are we doing? We are changing xj's equation by a following new equation. Okay. So this is the do notation for denoting the new joint distribution over the variables, which is entailed by changing one or more structural equations. It's good. So, as I think I said multiple times already, this new graph C tilde should induce a DAG. But other than that, you can do whatever you want. Okay. And you can completely change the thing to be something completely unrelated. So, but there are some types of interventions that we care about, and I'll just stick to a few classes of interventions in the discussion for the next few days. So deterministic and some types of stochastic interventions. You can also simultaneously intervene on multiple variables, but I'm not really going to talk about it. The first special case is something called the atomic intervention or a deterministic intervention. It means in the DAG, you take a particular node, say x2, you delete all incoming edges to it, and just set this variable to be a constant value all the time. Okay. So that means in the SEM, you look at the equation of xj. It was previously xj is some fj of its parents, comma nj. We get rid of that and just say it's equal to it. That's all it is. So that's called an atomic intervention. So C was the original graph. C tilde is the graph with atomic intervention. And the way you write this is the joint distribution of x1 through x5. C tilde is C, do x2 equal to 5 of this. You mind if I close the door? Also, now it's clear from this, hopefully, that doing is not the same as conditioning, because I'm basically essentially created a new model. Okay, so they're completely different things. They may be the same. It may turn out they're the same in some cases, but in general, these things are completely different things. So hopefully that has come out clearly now at this point. Okay.
Question.
Yes.
Question of Zoom. So do you said you set it to A and you delete the edge. Like, doesn't setting to A, like, do you need to say both of those things? I mean,
yes.
or are they the same?
Following trend. You're saying setting it to A implicitly deletes the edges. So I'm just doing it explicitly to make the point that really what has happened when I say set it to A is gone back to the original structural causal model, deleted one equation, replaced it by a new equation. Correct? That's what I've done.
See, okay.
And therefore, the
got
graph you are generating is different. That's all.
Mm-hmm.
Okay.
Thanks.
So, yeah. Okay. So that's why we say setting to A is actually deleting the edges, because really that's what you're doing in the SCM previously. Okay. So this in the original model, conditioning is given x2 equal to 8. This is the notation we use for conditioning. This is the notation we're using for doing an intervention. And they're unrelated. But they can be the same. Let me qualitatively do it first, and then we'll come back and prove it in like maybe half an hour or maybe next talk. Look at this node. Okay, this has no parents. So if I condition on this versus do on this, qualitatively, it shouldn't change anything. Why? Doing affects all nodes downstream. Conditioning affects all nodes in the graph. Because when you condition, you basically say, I'm looking only at those samples which are consistent with my setting that value. Okay. So I'm restricting to some part of the state space. So this is a slightly deeper look at do versus condition. Okay. Do is a downstream operation. It doesn't it's not a joint it's a surgery on the graph not on conditioning on the distribution. Okay. So, but if the node you're intervening on has only downstream, then do should be the same as conditioning. And we're going to use this property later to actually derive many of the rules for intervention. So this is really why you can hope to get data from one observational thing and move to conditioning. You need to use this property carefully throughout. Yes.
What happens to X1? Do you think of it as downstream in this context?
If X1 is an upstream, X1 is.
What I meant was if you do a condition X4,
yeah,
does it affect X1? Because you were talking about it downstream, right? X1 is not
it's not going to. It will really affect this. Okay. In this figure, but we'll get more formal in just some time. I'm just giving you a heads up of saying even though this is not equal, there are cases where this could be equal. And the intuition you should have in mind is this, that conditioning affects all nodes in the graph, irrespective of whether they're neighbors or not, because you are just changing all the samples. Okay, the distribution of all samples. Okay, fine. Second is a soft intervention. So this is also done a lot in practice. A soft intervention or stochastic intervention is the following. I look at this and I will change. So this, if you look at the Markov factorization of this graph and just look at this part, there's some equation of the form P x3 given x1, x4. I want to change this function. That's a soft intervention. I'm not changing the structure. Okay. I'm not changing the structure. I'm changing this relation. This case. So what does this mean? In the structural equation model, x3 is equal to f tilde j, that's change, of PAJ, that is still the same. I'm not changing the PAJ, comma n tilde j. This is what a soft intervention is. A special case of a soft so there are other interventions we could do as well, which we'll look at. An intervention of the form, instead of deterministic here, cut this and replace it by nj tilde. That's also another type of intervention we will do. It's a form of soft intervention as well, meaning xj will be set as nj tilde. That's another intervention. It is not keeping the same structure, but it's somewhat it's a random. So that's useful because that's really a blind randomized trial. Okay, that what we talked about. That cut the incoming edges and just choose a random, that set it randomly is just a treatment randomized trial. That's all. Good. So for the kinds of interventions we are talking about, there's another way to represent this, which is useful for all the proofs we'll do in like tomorrow, or the calculations and proofs we are going to do tomorrow. So let me talk about a different way of representing these interventions. So the kinds of interventions I'm going to look at is at a single equation, switch it around. You could do multiple as well. This model allows it, but I just want to think about single node interventions. It just keeps things easy. Again, there's no loss of general. The loss of generality is because of my explanation. It's not because the modeling doesn't allow it. Okay, let me put it that way. So this is my graph. What I can do is for every node, I can associate an intervention node. So this is a new graph I'm creating, C star. Okay. So for every x1, I'm putting an incoming directed edge, I1. For x4, I have an I4 and so on. I'm putting a square box around it just to say that this is a fictitious node that we have created. In reality, on this graph, everything is really a round node. Okay. Just new nodes. I've just created new random variables. And we are defining the following. Xj, and this random variable can have an idle or non-idle state. Okay, the non-idle, when it's not idle, if it takes some values in some alphabet, it can take whatever. So let's say just it can take some random variable ij or whatever alphabet you care about. But this essentially encodes intervention. if this is set to idle, if any node is set to idle, the structural equation model for xj is what it originally was. If it is set to, if it is not idle, it will take that value. So this allows soft interventions of a certain type, right? So meaning, let's look at this node. If this set is set to idle, this is the graph effectively. If this is set to some value, this is what happens. Okay. Meaning, actually, this is what happens. Okay. When it's not idle. That's so this is one way to encode interventions. Okay. So when it's active, encodes the intervention. So maybe ij can take values over whatever the alphabets x originally had. Okay. Suppose you wanted to encode a hard intervention this way, I to some value a, then ij would be either idle or a. Okay. Any hard intervention then would come down to this would be either a when this is this. So where ij it belongs to a comma idle. That's all. And you can encode other things as well this way, right? I'll just stick to hard interventions, but you can do other things as well. In which the important thing to notice is the following. In this graph, conditioning on this node is the same as intervening in this graph. Okay, because as we just saw, doing and conditioning are the same for nodes with no parents. Okay, so I can reason through standard conditioning on this graph and reason about interventions in this graph. Okay, of course, the joint distribution in C star is different from that on C. Basically, I've just pushed the problem elsewhere through this encoding. The problem has been pushed to this augmented graph, but at least the machinery for dealing with conditioning is something all of us are much more familiar with. So this mapping allows us to think about it carefully. That's all. So,
Question.
yes.
Can I do complicated intervention?
Yes.
I don't know this.
You
I
can.
don't want to set it to 5, but I want to make my intervention at x2 is that x4 is same as x2. So will those in the equations I can do whatever, right? I'll erase f2 and then say x2 is
You
same.
can put more complicated graphs.
Oh, I see.
Okay. But I will, yeah. Yeah. But for what I'm going to do is I'm just going to deal with atomic interventions. So summary of our discussion is the following. Look at some target variable y. Okay. So think of target variable as some downstream variable here. Okay. Suppose I want to marginalize out my distribution on this for the following. Take the original model, do some intervention on xj. I'm going to intervene on this variable. And I want to find, in this new intervention, I want to find the marginal distribution of x5. Okay. Look at questions of that form. Okay. Why do we care about it? The kidney stone was those kinds of questions. I want to find the effect when I intervened on the treatment to force it to be a small puncture surgery, and I want to find the effect. That translates to marginalize out on some target variable on the original graph, but with an intervention where some node is being set to something. Well, in this case, this is the same thing as looking in the C star graph, condition on that ij takes the value ij, look at the conditional distribution of y given that, because of this mapping. Of course, this distribution is not the same as this distribution alone. But with the do, it's just been encoded here as condition. Good. So so this is yet another story which I thought was interesting, which is it's like the kidney stone kind of thing, but I thought it's just worthwhile to see this. It's just a fun story. Well, I don't know about fun, but it's a story. we should be careful about the fun. I don't think myopia should be called fun. Okay. Sorry, somebody had a question on Zoom.
Yeah, I had a question about the augmented graph. So until now, the original graphs, when I was thinking of the FCM and the probability distributions, like I would go back to the what are they, the top nodes, and then if they don't have parents, I can just multiply the unconditional probability of those nodes. But I was imagining that the joint distribution has those probabilities, unconditional probabilities, in there. But now these I variables, I don't have any idea of probabilities on these variables.
Okay. So
right?
I am not going to do any. This mapping is not very useful for dealing with real data. It's just useful for doing proofs.
Okay.
I
Okay.
use this mapping just as a proof technique. When I'm going to do proofs when I want to show that some adjustment theorem on this, I will use this for reasoning about doing the calculations. That's all, intermediate.
Okay.
It is not used for anything other than that.
Okay, great. Thanks.
Okay, so let's go back to this. So this was a study between night lights, child myopia, and parental myopia. Okay, so this is a paper in 1999, and this example is in the book. If you want to read much more detail, 611 is the textbook example. It showed that dependence between night light and child myopia with caveats. The paper said the statistical strength of association ellipses suggests absence of night light is a factor in development of myopia. This is a certain ellipsis. If you want a more careful ellipsis, go to the book. This is even more ellipse. It's a much sharper ellipsis than maybe what the authors intended, but this is an ellipsis nevertheless. Okay. The question is, yeah, so okay, night light and child myopia. There's some potential dependence. So is there really a causal effect between night light and child myopia? The answer was that no. Future studies actually show that parental myopia is the true source of the correlation. Parents with myopia more likely put night lights in child's room, okay, because they couldn't see. So this statement says, is this weird thing. You put a night light, your kid is going to have myopia. Okay, so you should not, that's basically what this basic statement seems to suggest. And so this was the true causal graph. And so what we want to do is to check for this causal effect, which means what we want to do, check for this causal effect, night light, this thing. So what we want to do is to do an intervention here. So this is really the study. So I'm just tying back to what we want. What we should do to test this statement is somehow do this cut, set this to a value, and then check whether what effect you have. Meaning we want probability of child myopia. Really, this is what we want to ask. Look at the night light. The experiment we want to conduct is, it can be dark, maybe low light, maybe room light, maybe multiple states. Maybe 2 is enough. Maybe you want to do 3 states. And then you want to check the following with set different values of the night light and find the probability marginalized on the child myopia when you have done night light with these things. If these are exactly the same across then you know that this arrow is not present. Okay, that this statement is not true. And just tying back the formalism we've developed back to a concrete example. That's the only point of this example. Okay. Or equivalently, another way to do this is put a random variable which takes probabilities 1/3, 1/3, 1/3 with ABC, and we can look at the graphical model with this do. I set the equation for night light to be equal to this random variable. This is basically a randomized trial. That's all. Okay. And in that, if there is no causal effect, if in this do, you can check that these quantities are exactly the same. Excellent. Okay, so this motivates now the definition of causal effect. Okay, we have been using this word multiple times. So this is a formal definition.
So how did that paper come up with the fact that there is no causal effect? Because did they actually do this randomized control?
Somebody else. So
they did.
yeah, this was for some other paper. Go to in the, you can get
It's
more
not
details.
difficult to do this.
Don't ask me. I didn't dig through the. I didn't do either the test nor this thing. I'm just using this as an example. You can take it up with example 6.11, page 90 to 91 in the text. And who will point you to somebody else? Okay, so. As I said, I'm just giving you examples here. Yeah, I haven't done any of the experiments. Total causal effect. So all this now allows us to define total causal effect. A total causal effect is a directed, first of all, this is a directed action. Okay, it exists from xi to xj. So basically, we are looking for this. This is what we are looking for. If and only if, this is the definition of total causal effect, there exists a random variable n xi tilde, meaning we are going to do this intervention. We are going to change the SCM with this equation. And xi is not independent of xj in the joint distribution induced by this two. That's the definition of total causal effect. Personally, I like a different definition better. I'm going to get to this, but I just wanted to put down the basic definition. I know it may be a little fast to parse. I'm going to parse it once more quickly again in a different way. Okay. This is the definition that connects causality with independence with respect to an intervention distribution. So we are doing and this relation is directional. There are 4 equivalent statements for total causal effect, some of which are much easier to sort of, I think, at least for me, qualitatively see than others. Okay. For a structural causal model, the following 4 conditions are equivalent. There's a total causal effect from xi to xj. Okay. 2, there exists a pair of atomic interventions such that when you marginalize on xj, after doing xi is x1, that's different from the marginalized distribution xj when I do xi equal to x2. This is the definition that makes most sense to me. Okay, I do something upstream, and that changes the distribution on something on the other node. I do something else, it changes the distribution. That means doing the atomic intervention there has an effect. This is the way sort of I've been motivating causality in some sense. So this is the definition. There exists an X such that the intervention distribution is different from the original distribution when marginalized on xj. That's another way to show this. Third, xi is not independent of xj in this graph. Okay, when I do a randomized trial, after randomized trial, we see no independence between those 2 variables. That was the original definition I stated for TCE. And the proof is that look at the proof is an appendix of the book. You can read it. I'm not going to show the proofs, but these 4 statements are if and only. All 4 statements are equivalent. Okay. Yes.
What is 1? 1 is same as 4, right?
1 is the definition. No, 1 is 4 from definition. 1 is equal to 4 for definition. So this is another way to, this is the combined definition and a theorem statement. That's all. Okay. Finally, we want to connect graph structure with total causal effect. Okay. If there does not exist a directed path from xi to xj in the DAG associated with C, then there is no total causal effect from xi to xj. Ideally, you'd like the positive statement, but that's not this. The faithfulness is not going to allow us to make it that way. Okay, so let me repeat this statement. If there is no path from xi to xj, then there is no total causal effect of xi and xj. The converse is not true. So let's look at this. So let's look at let's look at this. I'm trying to see if there's so there's a clear X1 has a causal effect on X5 potentially, okay, as a total causal effect on X5. Why I should I do interventions here? I should be able to change the distributions here. Potentially, okay. This is what we'd like to say, okay. But that's not what we are saying. We are saying a slightly weaker statement that if there is no directed path, then there is no total causal effect. But it's not saying when there is a total causal effect. The reason is because of the same example again. The X1 and X2, there is no total causal effect in spite of the fact there's a directed path if it happens that C plus AB equal to 0. Okay, this was our faithfulness violation example. Okay, so that brings me to sort of an overview of what have we done so far? We have defined the SCM, we have defined what interventions are, we have defined what a total causal effect is. Okay, and we also have introduced a model for reasoning about interventions, though we haven't said why. Good. Have about 5 minutes. So let me just start talking about the calculus of interventions, and tomorrow we'll continue with that. So the goal is now we have a known structural causal model. It's associated DAG and a Markov factorization. We are going to look at interventions of this time, either atomic or random variable. I'm going to take one of the nodes, prune all its incoming edges, either do an atomic intervention or set it to be a random variable. We can do other things as well, but I'm not going to talk about other things. You can go back to the text for more details. And what we want to do is to compute the intervention distribution using only observed distributions. We don't want to do any new experiments. And we want to see when we can do this. That is going to be this section. Okay. Okay, let me just start by talking about an important observation that's going to allow us to do these calculations. Let's see the original observational structural causal model, C tilde be the one with the intervention. For concreteness, on the node J, we're just doing N tilde J. That's all we're doing. And this is independent of everything else. And let the distribution of this random variable be P tilde. So the original one is P, this one is P tilde. So let's look at this graphical model, to the original graphical model C. So look at the joint distribution on X1 through XD, or the variables there. Well, we know Markov factorization, it is of the form P for the C distribution for any variable Xi, condition on appearance of Xi is a product. That's a joint distribution. This is observational factorization, distribution factorization. Similarly, let's look at for C tilde. So what has happened in C tilde? Edges have been deleted for Xj and instead replace that by a random variable independent Nj tilde. So the joint distribution with C tilde is just using our do notation. There's nothing else happening in this first line. It is C with a do on that particular node of the same variables. If you notice here, the factorization of every other node in this graph is unchanged from the original graph. So, which means PC tilde can be written as, for every node other than J, you can still write it as PC of Xi. The functional form is exactly the same of PC Xi given P parents of I, except for the Jth one, where you have previously it was P of Xj given Paj. Instead, we have replaced it by P tilde Xj. So these two distributions are closely connected. Now, if you look at this, you can see that there's really one term that is different. And that's really what we are going to use to reason about how to marginalize things out correctly from one and get a reason about the other one. Okay. And in particular, if this was not a random variable but atomic intervention, this would simply be indicator Xj equal to A. Okay, meaning it's a 0, 1 variable. If it's 1, it's equal to 1 if it's A and 0 otherwise. Okay, that's all that would happen for this distribution. Okay, it'd just be an indicator function. And these things are called the truncated factorization theorems. I mean, it's almost immediate. There's no theorem here really, but that's what this is called. It's you just look at the graph and say this follows because of just factorization. Next thing I want to prove is conditioning equal to do for nodes with no parents. But I have only 3 minutes left. So I think this is a good place to stop. And we'll continue from here tomorrow. Thank you.